change to a originally scheduled program. Mike's going to wrap up for us with a Ronald Reagan-inspired hour-long polemic. No, I have no idea. I've heard you do this sort of thing before. I assume there's prizes.
There are prizes.
Yeah, there are prizes. So I think I've said enough. I will step out of the way. Everyone knows who Mike is. Thanks,
Nick. Yeah, so first of all, as I'm the last speaker, I'd just like us to acknowledge the wonderful effort that Vince Moulton has put in as main organiser of this meeting and indeed of the whole program. Thanks.
Why don't we just thank Mike and Daniel and Vince?
So I should say this talk has been cobbled together at the last minute with bits and pieces of earlier talks and a few hastily made slides. But as I was coming here on the long flight from New Zealand with not much better to do than sit there and read, I discovered this wonderful book. And we've had a lot of talks about phylogenies and so on, but this book is great because it's written by a biologist and it tells no fewer than 68 little stories, short stories, ideal for the plane, on why phylogenies are useful. What great things they tell us about life and so on, how they're being used. It's a great sort of source, perhaps for students or for those teaching students who want to kind of show how phylogenies are used in myriad different ways. So there's no mathematics in this book at all. John Avice is a biologist, but I think it's...
Who's the author, mate?
John Avice, A-V-I-C, yep. Okay, so so the first topic is joint work with Eric Mattson, and we had this comment yesterday that how lucky biologists are because they get to go out and do field work. Well, actually, mathematicians do also get the chance to go out and collect rare alpine plants and so on. So this is joint work with Eric Mattson, who was with us in New Zealand. And it was published earlier this year in MBE. So just to a little bit of background about this problem. We all know how Bayesian phylogenetics works. You have some data and you have priors on trees and priors on the branch length. Now the very simplest Bayesian scenario, you would have just 3 trees, and in which case if you have a molecular clock imposed, you really only have 2 parameters, the length of this branch and the length of this branch, because the length of that branch will be the sum of both of them under a clock. And you have your data and you say, well, what is the, if for example each of these trees was equally likely, probability 1/3, and you have some prior on the branch lengths, you can say, what is the posterior probability of my tree given the data I see? And of course by Bayes' theorem that's just proportional to the probability of the data given the trees integrated with respect to the prior on the branch length. So this is the posterior probability of this tree conditional on the data written in this form. Now this prior on the branch lengths, we have many choices. Often people make the assumption that T0 and T1 are independent, and sometimes they might suppose that the prior is exponentially decaying or uniform or whatever. I'm going to look again at the very simplest scenario where you just have the 2-state symmetric model. So you have 2 states, 0 and 1. This is the model, for example, Eric talked about. And your data then can really be thought of as just 4 numbers. The number of sites where you have 3 zeros, or where the 3 things are the same. The number of sites where 1 is in one state and 2 and 3 are in a different state, and similarly the number of sites where 2 and 3 are in a particular state and the other 2 taxa are in the other state. And if you sum those up, you get the sequence length. So your data, your line sequences compressed down to these 4 numbers. And I'll just, rather than writing a probability of T1 given the data, I'll just call that P1, and similarly we'll have P2, the probability of the second tree, and P3. Okay, well that's all can be found in any textbook from probably 10 or 20 years ago. What is the star paradox? Well, imagine that actually the data is generated by a star tree, that is a completely unresolved tree with some particular branch length. Now this branch length T1 I'll think of as a fixed branch length. I mean, it could be randomly chosen, but let's just think of it as fixed. So the data, I generate insights, IID, from the star tree, and then I say, well, how much support am I going to see for these three trees? And now, of course, this number here, this probability is going to be a random variable because this data is going to depend on what the star tree produces. But somehow your intuition might lead you to suspect that as the sequence length gets very large, we'd somehow hope or expect that the posterior probability for any one of these resolved trees, say this one, should go to a third, the same as the prior. Somehow that we shouldn't see strong support for any one of these trees if the truth is really a star tree. So we can ask this question: what is this? Is this true or not? And in fact, we could ask an even more clever question, which is what is the joint distribution of P1, P2, P3 as the sequence length gets very large? Okay, well, you know, if we assume exponential independent priors on T0 and T1, we can, you know, in theory, we can sit down with a big piece of paper or several blackboards and start doing calculations. I mean, it is possible, but, you know, it's not easy. Very few people have really had the stomach to do this. However, there is one man who has really taken the bull by the horns here, and that is this gentleman, Zhiheng Yang, down in London, who really got stuck in and tried to calculate the distribution on the posterior probability. And he published, together with Bruce Ranala, this nice paper in EMBO back in 2005. And so this is the plot of these posterior probabilities, P1, P2, P3. So along here, for example, you'd see this is P1 going from 0 to 100%, P2 going from 0 to 100%, and P3 going from 0 to 100%. So you see that when you simulate 20 sites, now blue here is high and red is low. You see a lot of, you know, what you'd expect. Most of the support is in the middle. And as you increase the number of sites, well, you're still getting the support, but it's kind of spreading out a wee bit. And you go with a few more sites, 1,000. And at this point, although Zhiheng was trying to do these calculations, he was having to use approximations and so on because it does get computationally tricky. And he made this comment that they encountered problems using Mathematica for large n, and it is unclear what the limiting distribution is when n goes to infinity. So, but he was able to do bootstrap, so that is where you have your sites and you resample the same number of them, and you can say, well, what percentage of the time do you find the same tree? And he was able to do those quite easily, and somehow there's this connection between bootstrap and Bayesian, and he found that, interestingly, there was quite a lot of support in these corners. Now that's saying somehow that there is some strong support for these particular trees when the data is generated by a star. So that seems a bit weird. So then along comes Kolkowski and Thornton. We've heard about them already. They were the more for the other paper that appeared in Nature. But this paper, they sort of took issue, I guess, with this paper of Ranala and Yang, and they made this comment that, so what they decided to do was, they said, well, it's really hard to do these calculations. Let's just imagine our data is really infinite, and then do the posterior probabilities with the exact frequencies you would get if the sequences were infinite, but using just finite length pretending they were a finite length. And they made this comment that with infinite length data, posterior probabilities give equal support for all resolved trees, and the rate of false inferences falls to 0. We conclude there is no star paradox caused by not sampling unresolved trees. Okay, so they did these simulations, and they found this is the unrooted equivalent of a star tree. They found indeed there was this exact 1/3 figure. So it was sort of somehow looking, well, maybe there'd been a mistake in the simulations or something. They made this comment that the analysis of ideal data sets does not indicate what will happen when very large data sets with some stochastic error are analysed, but it does show that when infinite data are generated by a star tree, posterior probabilities are predictable, equally supporting each possible resolved tree. So I guess the impression here is that somehow in the limit things are fine, therefore when things are large, things will be fine too. And this is one of those most of the time that's probably right, but this is one of the interesting cases where it's not correct. So let's just get maybe some intuition for this. I'm not going to try and give an intuitive explanation for what happens in this Bayesian setting, but let's see why in the bootstrap setting you get support for these resolved hypotheses when the data is unresolved. And rather than working with trees, let's look at something much simpler that we all know about from our first year at stage 1 statistics, tossing coins, right? So imagine you have a coin and you're trying to test two hypotheses. One is that heads is slightly heavier and more likely to come up. The other is that tails is heavier and more likely to come up. And P being here the probability of heads. But suppose actually that the coin is perfectly balanced. It's a fair coin. So neither of these is correct. Okay, so you toss your coin, I don't know, 30 times or so, and you'll have some sort of, this would be the histogram of the possible proportions of heads you might observe in those 30 tosses. It'll have roughly a normal distribution. And now it could be, of course, that you see that you get some, a real preponderance of heads. That could happen. And now when you do bootstrap, you've taken all of, imagine you've recorded all of those tosses of heads and tails, so you wrote them all down. So maybe it was heads, tails, head, and so on, 30 times. And then you independently and with replacement resample from this sequence, and you say, well, what proportion of the time that I do that do I see a preponderance of heads coming up more often than tails? This is saying how often does the resample data support H1. And of course that will also have a normal distribution. It will have, this is its mean, the proportion of heads in your sample. It'll have a slightly different standard deviation, but somewhat similar. Okay, and so the thing you'll notice though is that it's actually, if your original observation was out here, it's then going to be quite likely that you're going to see, the proportion of bootstrap replicates that support this hypothesis here is going to be very large. It's going to be everything except what's out on this tail here. Okay. Now, of course, if we had chosen to start with, instead of 30, if we'd chosen an infinite length sequence with a complete balance of heads and tails, and then done the story, but resampling just subsets of 30, this wouldn't happen because we'd be exactly at this point, and we'd have a distribution just like this. It would have 50% chance of supporting H1 or H2. That was what Kolkowski and Thornton essentially did. They said, well, imagine you stick in the what happens if you had an infinite sequence, but then do the resampling just a finite number of times. Now this effect here that I've showed, that you only get into trouble, or you only see support for H2 out there, you might think, well, maybe it disappears when the sequences get long. And you see that really it doesn't. Suppose now I toss this coin, as someone did when they were in a prisoner of war camp, tens of thousands of times, and record this. Now my standard deviation will be much less. So I'm going to be much closer to here. So you might think, oh, well, it's going to go away. But it's not going to go away because now the standard deviation of this thing is going to be much less as well. So this area out here is about the same as what it was over there. So it doesn't vanish as the number of tosses gets large. It's because both things, the number in the original number of tosses and the number in the resampling is the same, that is crucial here. So Eric and I, so we didn't look at this. We didn't look at coins. We did it initially to try and get some good intuition. And we didn't look at bootstrap. We went into the Bayesian thing and we said, okay, well, Yang assumed independent exponential priors. Can we actually have a more general theorem that just makes very few assumptions about the prior? All we really want, we don't even want to assume T0 and T1 are independent. We probably need some assumptions on the prior, but really all we needed was that the prior is bounded and smooth, and that's about it, really. And such a prior we call tame. So we got this result then that if sequences of length n are generated on the star tree with positive finite edge length T1, then for any tame prior, that is a prior on the branch lengths that's bounded and smooth, and for any epsilon there, the following property holds. The probability that the data has the property that the posterior probability for T1 is large. You know, it might be, you could take epsilon to be 0.01, so there's going to be 99% support for T1. That probability doesn't go to 0 as n gets large. So there's always going to be a chance you're going to see trees that are strongly supported even when the data is generated by an unresolved tree in very general conditions. So it was a lot of fun playing with that. And one of the nice things was we avoided having to get into the, if we had actually worked with the exponential, even with independence, it would have been much messier because the calculations are very difficult if you try and do them exactly for a particular case. But if you do them more, it's one of those interesting situations in maths where the more general result is easier to prove, I think, than the more particular result. Now, just in the last month or two, I think it's just come out in EMBO, this further paper by Zhiheng Yang, where he's got around some of these approximation problems. This is quite a long paper. He's really, again, done some very interesting work, and he's been able to resolve this problem he had earlier, and this is now what happens for really long sequences. It's not the exact solution. Again, there's approximations involved. But this is the plot, again, of the posterior probabilities, and you see there's this blob in the middle, but now there's definitely these blobs out on the corners there. And if you look at just the posterior support for tree T1, he's able to get a good approximation for this. And you see that, if there was no star paradox, you just expect everything to be on 1/3, to be concentrated around 1/3, but it's spread out. And so I guess this result of Eric in line with is saying that this doesn't drop down to 0. It sort of stays away from 0 as you approach 1. But of course, this result is very particular to a particular prior and independence between T0 and T1. Okay, so the first math, the 6 math challenges. This is the first one. Compute exactly the limiting joint density for P1, P2, P3. That's still unsolved, as Zhiheng Yang pointed out in his paper. Or even just, what is the form of this function in the limit? It must have some, well, I won't say it must, but it should have some nice mathematical description. Okay. So now, before Benny usually chips in at this stage and says, what's the reward? Okay, so there is a reward. It's, of course, a bottle of fine New Zealand Oyster Bay Chardonnay. There we go. Okay, networks. Well, we could probably list about 20 really interesting problems with networks. I'm just going to choose my 2 favorites at the moment. Bi-tree nets. What are bi-tree nets? Well, this is the name I just invented late last night. We all know that if you have a tree, you can encode it with its set of splits. And well, you all know that. Okay. If you have a second tree, of course, you can do the same. And if you have 2 trees, of course, you can take the union of their splits. And so in this case here, if I do that, I get, I can represent the union of those splits by these networks. So I see, and this has some biological relevance, because often you see two trees in your data, one way or another, whether it be through lineage sorting or horizontal gene transfer or whatever. Often two trees is an interesting sort of network. Now you might ask, we know that if I know the splits of a tree, I can get the tree back. If I know the union of the splits of two trees, can I get the two trees back? Now, there's no prize for that. The answer is no, but you have to search a little bit. But this is an example of two trees and a different set of two trees that have the same set of splits. Okay, now yesterday we had this very fine talk from Andreas Spillner on computing the phylogenetic diversity of a split system. And I won't go through all the definitions again. We had a few talks on phylogenetic diversity. But here's a really interesting question, which I think, or I hope, is still open. What is the complexity of finding a max PD set of given size on bi-tree nets? So if I take the union of two trees and I splits, and I want to say, and I give you a number k, find a PD set of size k that maximizes the phylogenetic diversity. We know that for a tree this is easy. The greedy algorithm works, as we heard yesterday. And Andreas told us yesterday that if you have a circular system of splits, it's also polynomial time. So you might ask, well, maybe that solves it. If you have two trees, is the union of their splits circular? Well, often it is, but unfortunately it's not all the time. There's an example here of two trees for which the union of the splits is not cyclic, so we can't use that example. Oh, okay, it's time to pull out the second bottle of wine, I guess. So just while we're on bi-tree nets, I think there's a whole raft of interesting questions here. I mean, here's another one. What's the complexity of finding a maximum parsimony tree if I have the splits of two trees, which I think of as binary characters, and I just concatenate them? Very natural question. We know that finding maximum parsimony trees is hard. If I had just a single tree, I would know what the NP tree is. It's that tree. But here I've got two trees. Now, it might be that this is a hard problem, but maybe if I say the two trees aren't too different, maybe one tree is an SPR of the other, and that could be relevant too, because if you have a horizontal gene transfer, that corresponds to an SPR move. So if we're thinking of these two trees as being arising from something like a horizontal gene transfer, this restriction maybe would still be biologically relevant. Okay, here's another question on networks. There's been a lot of work on what are called Gould networks, which is sometimes also called level 1 networks. What is a level K network? A level K network is a network where every bi-connected component has at most K reticulation nodes where two or more edges come in. So this network is a two-level network, because this component here has two reticulate nodes. Okay? A zero-level network is just a tree. A one-level network will look something like this. We have a tree, and every now and then we might have two things coming together, but we don't have. These are somewhat isolated, if you like. We have these sort of cycles here and there, where we don't have anything more interesting than just two things coming in. Okay, so now we've heard in several talks, including one this morning, that one way of building up these networks is to look at rooted triples. So suppose you have the triple, say, in this case, ABC. So that triple is consistent with this network because, you see, here's A, B, and C. This tree, A, B, and then C coming down like this, sits naturally inside that network. But so too does the tree A, B, C, a different tree on the same set of three leaves, because if I go up here and I come down, there's the branch leading to A, And I come down here, there's a branch leading to B and C. So those two rooted triplets are consistent with this network. And suppose now I have a set of rooted triplets, and if I say nothing more, the problem of even determining whether there is a level 1 phylogenetic network that is consistent with that set of rooted triplets is already NP hard. However, if I say that for every 3 species I have at least one tree, so that the set of rooted triples is in some way dense, okay, for every 3 species I have a tree, if I have that, then there is a fast algorithm for determining whether there's a level 1 network, and these guys from the Netherlands have just shown there's also a quite complicated polynomial time algorithm for determining whether there's a level 2 network. However, they have, it seems, no idea from talking to them a few days ago that whether this problem is polynomial solvable or not. Is there a polynomial time algorithm for the following? You have a dense set of rooted triplets. Dense, remember, means every set of 3 species you have at least one tree for that 3, and some integer k, and you say, is there I should have here, is R consistent with a level k network? Okay. So I think it's a very fascinating question that to look at. So okay, so here we go. In this room. It was a very expensive visit to Sainsbury's yesterday. Right. Okay, so the last part of this talk is, again, something I cobbled from a talk I gave in the United States shortly after George Bush was re-elected, and I've taken out most of the more inflammatory parts of the talk, of the weapons of math instruction and so on, but this is really sort of trying to deal with some of the errors that arise in phylogeny reconstruction, and we've of course had much discussion of many of these, and I'm not going to, I'm really only going to look at this question of how much data do you need to reconstruct a tree. And we all know there's difficult phylogenetic problems where you have some deep divergence in a tree. You've had perhaps some short period of rapid radiation, and then you've had long periods of time where any signal in there has probably been obscured by back substitution, site saturation, and so on. To a mathematician, I guess the way to view this is that you're trying to figure out what was the tree that connected these monophyletic clades, these groups, and maybe it was just a very short period of time for the speciation to occur, but there's subsequently been a lot of change out here. These are the sequences we see today. I drew this tree upside down because I was talking to biologists, of course. They seem to like their trees drawn like real trees are for some strange reason. Now there is a viewpoint that short edges are unimportant, and we had a very, that could be true in certain cases, and there was a nice talk yesterday about how you can, reconstruct trees and collapse short edges. And although that's often the case, I think sometimes biologists really are interested in short edges. Some of the biggest controversies in biology have revolved around, these questions of, what split off first, that or that, and so on. And I think, it's sort of, sometimes there are cases where really it does matter whether you're within, epsilon or not, because just being close enough is sometimes not good enough. Okay, so just carrying on then, the idea here is you have, if you have this tree, and you have a short interior edge, the sequences it generates will look very much like the sequences that this tree will generate. And we can say, well, as epsilon gets small, how would the sequence length have to grow as a function of epsilon? And the same thing out here. If you have long pendant branches, the data that this generates will look the same as this. Okay. Well, we know from some work some years back that for finite state models like DNA models or amino acid models, that the sequence length has to grow at the rate 1 over epsilon squared, where epsilon is this interior branch length, to distinguish this tree from one of the nearest neighbour rearrangements of it. And this bound applies for any method. It's not just that, it's true for parsimony, so we need to find a better method. It's actually provable that any reconstruction method must do this. Now these long pendant branches, you can try and break them up, and it doesn't really affect this 1 over epsilon squared at all. Curiously, if instead of a finite state model, you have an infinite state model, so every time you change to a state, you go to a new state, you have no homoplazy effectively. And these models have sometimes been invoked in looking at things like sines, short and interspersed nuclear elements, and so on. You have these different relationship, 1 over epsilon. So it's curious that you actually have a qualitatively different relationship between sequence lengths and branch lengths in this infinite state model case. What about the dependence of the sequence length on the number of taxa? Well, it has to grow at least logarithmically with the number of leaves. But one of the most interesting things, I think, in the theory of these Markov processes is that under certain conditions, it's been proved that you can actually achieve this as well. If you put restrictions on the branch length that they're not too short or not too long, then a number of people, including Tandy Warno, but more recently Alcan and Marcel, have really been able to establish some quite spectacular results there. So, okay, so what's the next challenge? Okay, here we go. What is the sequence length requirement for maximum parsimony and maximum likelihood? These results relied on constructing a method that you could prove a theorem for, okay, rather than a biologist coming and saying, here's a method, what can you prove? Okay? So what we'd like to do, I suppose, is the latter. Take a method like maximum likelihood or parsimony and say, what sequence length do we need? Now you might say, well, maximum parsimony is inconsistent, so how does this question make any sense? Well, of course, you need to restrict it a little bit for it to make any sense. I think answering the question for maximum parsimony is probably going to be a lot easier than maximum likelihood, but maybe I'm wrong there. Here's a conjecture, though. The sequence length you need for maximum parsimony, it grows at the rate log n over epsilon squared, provided the lengths of the edges are all less than x, which is some magical fixed number independent of n, about 0.05 or something. And the ratios of the lengths of the edges is bounded by some number b. That number b will enter into the constant c, and when we say with high probability, that means there's probability at least 1 minus epsilon. That epsilon will also enter into the constant c. Okay, so there's a conjecture. It will be interesting to explore. It has all sorts of consequences. I mean, an immediate consequence is the following. This consequence is purely combinatorial, that for any binary tree, one could construct about log n characters, binary characters, for which T is the unique most parsimonious tree. That would follow from this result by what's called the probabilistic method. If something has positive probability, there must be something there that makes it happen. And so if I put if I take a tree, put all of the branch lengths the same, less than x, I'd need only that many characters to have high probability that T is the unique maximum parsimony tree. That means there must be a set of that many binary characters, okay, because it has positive probability. I've actually said more. I've said high probability, but all I need is positive probability. So here's another challenge, and indeed you get the bottle of wine if you get this. Find a way of constructing from a fully resolved tree a set of order log n characters, binary characters, for which that is the unique most parsimonious tree. I can easily find a set of order n characters. I just take a split for every edge of the tree. Right? How do I do it for log n? So, an interesting question. Obviously, this is, well, I don't know which is easier. I mean, this is just an immediate weak consequence, I guess. Related question. In decision theory, there's this idea of admissibility. In the context of tree reconstruction, we say a method is inadmissible if there's some other method floating around for which the probability that your method applied to your data gives you the true tree, given the data was generated by that tree with some branch length, is at least as big as the probability that your method applied to the data gives you the tree. So this method is at least as good as your method, and sometimes it's strictly better. So that's what inadmissible means. Inadmissible means the method is not really all that flash because there's something around that's better. It's always as good and sometimes strictly better. Admissible is not necessarily a good thing because here is an admissible method for reconstructing phylogenetic trees from data. You give me the data, I screw it up, throw it in the bin, and return a particular fixed tree all the time, my favorite tree. Okay? So that doesn't sound like a very good method, but it is admissible. Okay? So inadmissible is bad, but admissible is not necessarily good. Right, so anyway, here's the question. Is ML, as it's usually implemented in phylogenetics, where you optimize the nuisance parameters, the branch lengths, is that admissible, or is MP, maximum parsimony, admissible? So one more of those. Okay, nearing the end, fortunately, for my budget. Okay, so I've talked about reconstructing trees, but you can sort of think of different versions of the reconstruction problem. Okay, reconstructing, you're given the sequence data and you're asked to find the tree. But you can think of other sorts of questions, like something Laszlo and I called teasing, which is you're given the sequence data and you're given 2 trees, or maybe 3 or 4 or whatever, but let's just say 2. You're given 2 trees and you're told, well, one of these trees was the true tree. Which one was it? Okay, that's teasing. And then there's testing. Testing says, given the data and you're given a tree, okay, I've got the data, and Daniel comes along with some tree and says, this is the tree that produced the data. In fact, this is basically what we had the other day. And we want a method that returns the answer correctly with high probability. What does correctly mean? It means that if it was the tree that produced the data, the method says yes with probability at least, say, 99%. And if it wasn't the tree that produced the data, it says no with probability at least 99%. Right, so we've got these 3 ideas. We can ask, what's the relationship between them in terms of the sequence length we need to answer these questions? And I think this is an area that's just really starting to be explored. We know some results, and I'll just mention 1 or 2 of them now. But the interesting thing often is that it seems that we need to discover some underlying combinatorics, some new combinatorics here. And just to give you a flavor for that, here is the man on the camel, but Eric promised we'd see, Laszlo Zekle from University of South Carolina. So when we were looking at this teasing question, we got completely stuck until we managed to figure out this result. Given any 2, it's a very strange result. It's very weird, almost kinky. So you're given 2 binary phylogenetic trees and they're different. I can always draw them like this. What does this mean? It means that in the first tree, I've got some subtree here that's exactly the same as this. This is exactly the same as that. This is the same as this, and this is the same as that. So if you forget about all those, so there's been, I guess, an interchange of these things. And these kind of muddy-coloured circles are just subtrees hanging off these connecting paths. They bear no resemblance at all to the subtrees hanging off that path at all. Right, so what's so stunning about this result? Well, the way I've said it so far, somebody would say, well, yeah, of course that's obvious, because if 2 trees are different, we know they must differ on at least 1 quartet. So why don't you take that quartet? Take that to be the leaf A, B, C, D, on which the 2 trees are different, and that would be true. So I haven't said anything particularly novel yet, until I say that these paths on the 4 pendant branches of T1 get subdivided at most 4 times, like this. 1, 2, 3, 4, here just twice. There could be a heap of stuff in here, and there could be a heap of stuff on these things, but these 4 pendant edges get subdivided at most 4 times. We know that 2 won't work. We don't know whether 3 works, but it doesn't really matter. It's the fact that there is a finite number. And what it's somehow saying is that if you have 2 trees that are different, there's some these 4 subtrees are somehow close. You know, these pendant branches aren't too long, which is important for things like site saturation. So what does this mean then? It has 2 immediate consequences. It means that under the finite state model, the sequence length you need to test a tree, that is this the tree that produced the data or not, it doesn't grow really with n. It's basically independent of n. And under the finite 2-state model, the sequence length we need to tease a tree is independent of the number of taxa. We know that the sequence length we need to reconstruct the tree has to grow. It has to grow at the rate at least log n in both of these cases. But this is a case where testing is definitely easier and teasing is definitely easier. The number of characters doesn't keep getting bigger with the number of taxa. And these results don't seem to follow from, well, certainly this one, without something like this result. We're assuming here that of course, that the probabilities of mutation on the edges are bounded away from 0 and from some upper bound. Okay, well, I just want to thank obviously my co-authors, the Alan Wilson Centre, the Newton Institute, and for you guys for listening. Thanks. Oh, sorry, I forgot the last one.
I volunteer to inspect these and check they're genuine.
Yeah.
Are there any questions for Mike?
Yes, Glenn.
To what extent is this question of inadmissibility related to the no free lunch theorem?
The what?
Like
The no free lunch theorem.
No, the no free lunch theorem basically says that over all problem instances, there is no single method that is always better than all the other methods. It seems like it's a very similar problem.
Well, there are situations where methods are admissible, you know, and if, for example, if for each tree we just had a single branch length and we weren't optimizing with nuisance parameters, then maximum likelihood would be admissible in that case. But yeah, I don't think it follows from. I don't think there's any general principle here that is relevant to this question. Maybe I'm wrong. I should talk to you later, I guess. Yeah. But actually, there is such a thing as a free lunch because Tandy gave me her Wilson court card.
We're all doing the problem. Like, this is the problem. We're talking and stuff.
They don't want to ask questions, but then you'll give hints
Yes.
about how to.
Right. They would be giving hints.
No
away.
giveaway.
Yeah.
Does anyone